These are the notes for AP Calculus on the topics of advanced L'Hopital rule problems and advanced disguised derivative problems. So let's refresh our memory on what L'Hopital's rule is. Remember, if you're evaluating a limit as x approaches some value, in this case a, and you substitute in a, you yield the indeterminate form of 0 divided by 0, then you can use the L'Hopital's rule, and what that says is you basically take the derivative of the numerator and the derivative of the denominator separately, and then you can substitute in a into those. So let's see how this works for some example problems. So on this first one, if we first substitute in 0, we get e to the 0 minus 3 times 0 minus the cosine of 0 over 5 times 0 minus 0 squared. Well, e to the 0 is just 1 minus 0. Cosine of 0 is also 1. That's 0 minus 0. So you get 0 over 0. So first, check and see if it's 0 over 0. If you just get some number there, then that's going to be your limit. But since we get the indeterminate form, that means we can apply L'Hopital's rule to figure out what this limit equals. And we treat the numerator and denominator as two separate functions. So we don't use the quotient rule. So I'm not taking the derivative of the entire thing, just the numerator and denominator separate. So let's start with the numerator. If you take the derivative of the numerator, the derivative of e to the 2x, using the chain rule there, since we've got 2x inside the x1. So e to the 2x, the derivative of e to the 2x stays the same, except we use the chain rule, we have to multiply by the derivative of 2x, function inside, which is 2. Then the derivative of negative 3x is negative 3, and the derivative of cosine x is negative sine x. So that changes that to be a plus sine x. And then if we take the derivative of the denominator, that's just going to be 5 minus 2x. And now we can substitute in 0 and see what we get. So we'll have 2 e to the 0 minus 3 plus the sine of 0 over 5 minus 2 times 0. So e to the 0 is 1, so that gives you just 2 minus 3. Sine of 0 is 0 over 5 minus 0. So you get negative 1 on the numerator, 5 on the denominator, so that's what this limit equals, negative 1/5. Now let's take a look at another one here. On this one, if you substitute in 1 for x, we get the natural log of 1 minus 1 plus 1 over 1 to the third minus e to the, when you substitute 1 there, that's going to be 0 minus 1 squared plus 1. So the natural log of 1 is 0 minus 1 plus 1 over, that's 1 minus e to the 0 is 1. 1 squared is 1 plus 1. So you can see you have 0 on the numerator, and all those 1's cancel out on the denominator, so you get 0 on the denominator as well. So again, we get the indeterminate form, indicated we can use the L'Hopital's rule. So again, we're going to take the derivative of the numerator and denominator separately. The derivative of natural log of x is 1 over x, minus the derivative of x is 1, derivative of 1 is 0. Over the denominator, derivative of x cubed is 3x squared, minus, now here we technically use the chain rule here, the derivative of e to the x minus 1, but the derivative of x minus 1 is just 1, so that doesn't change anything when you multiply by 1, so the derivative of e to the x minus 1 is just e to the x minus 1, minus 2x, the derivative of x squared, and then the derivative of 1 is 0. So now, let's go ahead and substitute in what x is approaching, 1 again, so that would be 1 over 1 minus 1 over 3 times 1 squared minus e to the 1 minus 1 minus 2 times 1. So that's just 1 minus 1 in the numerator gives you 0 over, that's 3 minus e to the 0 is 1 minus 2 also gives you 0. So what happens here, we still end up with 0 over 0, the indeterminate form after applying the L'Hopital's rule. That just means we have to apply the L'Hopital's rule again until eventually we won't get 0 over 0. So we got to take the derivative of the numerator and denominator separately again. And remember, 1 over x is the same as x to the negative 1. It's easier to take the derivative in that form. Using the power rule, that'd be negative x to the negative 2 over, on the denominator, derivative of 3x squared is 6x minus derivative e to the x minus 1 is, again, using the chain rule, e to the x minus 1 stays the same. When you take the derivative, the x minus 1 is 1, so times 1 doesn't change, and then derivative of negative 2x is negative 2. And simplify that, that's just negative 1 over x squared over 6x minus e to the x minus 1 plus 2. So again, let's go ahead and substitute what x is approaching, in this case 1. So that'll give you negative 1 over 1 squared over 6 times 1 minus e to the 0. We've substituted 1 there, minus 2. So you get negative 1 on the numerator over, that's 6 minus e to the 0 is 1 minus 2 gives you 3 on the denominator. So we end up with negative 1/3. So you may have to apply the L'Hopital more than once to stop getting the indeterminate form of 0 over 0. Eventually you won't get there. Now let's take a look at some that are a little bit different. And that's because we've got some definite integrals inside the limit. So let's start off the same way and see what happens. So first, try direct substitution. If we substitute in 1 for x, notice x is the upper limit. That'll be the integral from 1 to 1 of the natural log of t dt over 1 squared minus e to the 1 minus 1 is 0. But notice any definite integral, if the lower and upper limits are the same, that's just going to be 0 over, that's 1 minus 1, 0. So we do get the indeterminate form, so we can apply L'Hopital's rule. Take the derivative of the numerator and denominator separately. So when you take the derivative of the numerator when there's an integral already, that means we're taking the derivative of the integral from 1 to x, natural log of t dt. Now when you do that, notice you got the derivative of an integral. There's a constant right there, x is right there, so this fits the second fundamental theorem of calculus exactly. So essentially the derivative of the integral reverse processes, they cancel each other out. All that happens is the x replaces the t. So it becomes the natural log of x. Over, when you take the derivative of the denominator, that's going to be 2x minus derivative e to the x squared minus 1. It's going to be e to the x squared minus 1 stays the same, but using the chain rule times the derivative of x squared minus 1 is 2x. Using the chain rule, we have to multiply by 2x. So now let's go ahead and substitute in what x was approaching 1 and see what we get. So that'll be the natural log of 1 over 2 times 1 minus 2 times 1 e to the 0. So we get the natural log of 1, saying e to what x1 gives you 1, that would be 0. Over, that's 2 times 1, 2 minus 2, 0. So again, this is one where we have to apply L'Hopital's rule again. So let's take the derivative of natural log of x now, which is 1 over x. Right, the derivative of 2x, which is 2. But then when you take the derivative of negative 2x e to the x squared minus 1, overall there we have to use the product rule. So we have negative 2x times e to the negative x squared minus 1. Okay, so using the product rule, if we treat the first function as negative 2x, the derivative of negative 2x is negative 2 times the second one, e to the x squared minus 1 as it is. Normally it would be plus the first one as it is, but the first one is already negative, so it's plus negative 2x as it is. That's the negative, and then again when you take the derivative of e to the x squared minus 1, you have to use the chain rule, so the e to the x squared minus 1 stays the same, but then you have to multiply by the derivative of x squared minus 1, which is 2x. And then if we substitute in 1 there, we get what x was approaching was 1. 1 over 1 divided by 2 minus 2 e to the 0 minus 2 times 1 e to the 0 again when you substitute in 1 there for x. And then 2 2 times 1. So on the numerator, we don't get 0 this time, we get 1 over, that's going to be 2 minus 2, e to the 0 is 1, and then minus 2 times e to the 0 is 1 times 2 gives you 4. So you get 1 over, 2's cancel negative 4, so you get negative 1 4. Now let's look at another one of these. It's written a little bit differently. It's more of a general form here. It says let g be a differentiable function. If it's differentiable, that automatically also means it's continuous. It can't be differentiable unless it's first continuous. G of 2 is 5 and g prime of 2 is 4. What's the limit as x approaches 2? Let's go from 2 to x of g of t dt divided by 5 minus g. So the first thing you would do, again, substitute in 2. So for x, so that would be integral from 2 to 2 of g of t dt over 5 minus g of 2. Again, we have an integral from 2 to 2. On the lower upper limit is the same, that's going to be 0. 5 minus g of 2, they tell you right here. It's 5, so that's 5 minus 5 gives you 0. So again, we can apply the L'Hopital's rule and take the derivative of the numerator and denominator separately. So we take the derivative of the numerator. This is 2 to x. G of t dt. And again, notice the derivative of the integral. This fits our second fundamental theorem. This is a constant of 2 down here. That's x. All that happens, just like here, the x replaces the t. Same thing here, the x replaces the t. So on the numerator, we'll just have g of x over the derivative of the denominator. Derivative of 5 is 0, and then we got negative derivative of g of x is g prime of x. And then we can plug in what x was approaching was 2. So we have g of 2 over negative g prime of 2. G of 2 is 5, or negative g prime of 2, they tell you right here, is 4. We get negative 5 fourths. Okay, let's go on to the next topic now, which is advanced disguised derivative problems. So recall the definition of the derivative. F prime of x is just a limit as h approaches 0, where h represents the distance between 2 points on a graph, of f of x plus h minus f of x all over h. Remember, this just comes from the slope formula. And so when those 2 points get closer and closer together, when that gap between them approaches 0, this gives you the slope or derivative at 1 point. So what you have to do is just first recognize, okay, the limit as h approaches 0, arc secant of x plus h minus arc secant of x all over h, that this fits our definition of the derivative form. So this equals the derivative of some function. And you just have to figure out what that function is. In this case, you can see f of x is right here, this part of the formula. See, that's arc secant of x. And then you take the derivative just this way, rather than having to use the definition. So, derivative of arc secant, remember, is, doesn't start with cos, so it's positive 1 over the absolute value of x times the square root of x squared minus 1. And since this limit equals the derivative of that function, that's what this limit equals. Similar thing on this one. Limit as h approaches 0, e to the x plus h cubed minus e to the x cubed over h. You can see it fits this form here. So again, this limit equals the derivative of some specific function. This time you can see that function f of x is right here, e to the x cubed. So since this limit equals the derivative of that, let's take the derivative the easy way. This time, though, since we have a function inside here, we'll have to use the chain rule. So multiply by the derivative of x cubed is 3x squared. And when you take the derivative of e, that part stays the same, so it's e to the x cubed. Again, since this limit equals f prime of x, we've just found f prime of x, so this limit equals 3x squared e to the x. Take a look at one more here. So it says the limit as h approaches 0 of arc cosine of a plus h minus arc cosine of a over h equals 2. And a equals negative 2, then a equals. So on this one, we first have to recognize, okay, this fits our definition of the derivative. The difference though, instead of x, we've got a. We're trying to solve for a. So what this represents means it's f prime, not of x here, but of a. And we're told already what it equals, negative 2. So we just have to recognize again what f of x is. You can see right here, the arc cosine of x. A just represents the specific x value that's being plugged in. So we don't do that until we find the derivative. So arc cosine of x, and then take the derivative the easy way, the derivative of arc cosine, since it starts with a co, all the ones, inverse trig functions and regular ones that start with a co have that derivative as negative, so negative 1 over, just like arc sine, except it's negative, so it's square root of 1 minus x squared. So then f prime of a then would just be plugging in a for x, so it's negative 1 over square root of 1 minus a squared. And then you just have an algebra problem to solve for a at this point. So with this over 1, you can cross multiply. You get negative 2 square root of 1 minus a squared equals negative 1. Divided by negative 2. The square root of 1 minus a squared equals 1/2. And to get rid of the square root, square both sides. 1 minus a squared. 1/2 squared is 1/4. Actually, I'm going to add the a squared over to this side and subtract the 1/4 from 1. That's 4/4 gives you 3/4. And then take the square root of both sides. You get a equals, or take the square root of both sides, plus or minus. The square root of 3 over the square root of 4 is 2. So sometimes you can get more than one answer here. A could either equal positive or negative for all 3 over 2. And that concludes the notes for AP Calculus on the topics of advanced problems using the L'Hopital's rule and this guided through.